Alright, so today we're going to look at surface areas of prisms and pyramids. So total surface area, or TSA, so total surface area of a solid, so a 3D shape, is the sum, because it's a total, you add up all the surface areas. So the idea is, suppose you're trying to wrap a present, how much wrapping paper do you need, or how much cardboard do you need for packaging a Toblerone, or if you're painting the walls of a house, how much paint do you need? So essentially we're trying to look at how much area in total do we need for a 3D shape. To help us out, a net is a two-dimensional illustration of the surfaces of a solid. So that's what happens when you unwrap the 3D shape. So if you try to unwrap a tissue box, you get like 6 different rectangles, right? Or if you're trying to unwrap a Toblerone packaging, you get 2 triangles and 3 rectangles as well. So a net is just what you get when you unwrap your 3D shape. The third dot point, a right prism, is a solid with a uniform cross-section and the remaining sides are rectangles. Uniform, the word means, uniform means not what you're wearing, but uniform means the same. Cross-section is if you slice your 3D shape, that slice should always look the same. So if you think about the triangular prism, the Toblerone down below, how can you slice that triangular prism so you always get the same shape? Not the pyramid, the prism, the Toblerone one, right? So if you slice it vertically down, will you always get the same shape? No, because one, you'll get a thin edge of your Toblerone and then it'll get bigger and they'll get smaller again. On the other hand, if you slice it across and trying to get triangles every time, right, that horizontal across, that's the uniform cross-section. So if you slice it horizontally across every single time, you should get the same sized triangle. So that's what the uniform cross-section area means. So down below, that's an example of a right triangular prism. It's a prism because every time you slice it across, you get triangles. The other shape on the right is a pyramid, pointy bits. So if you have a pointy bit, that's an apex. It's a pyramid. Example 1. We have a rectangular prism and we have a pyramid because it's pointy. We're trying to find the total surface area of that. So literally add up the areas of every surface. So for part A, you have a rectangular prism. So you write surface area SA equals, because we're too lazy to write surface area, the whole word, just write SA is fine. If you look at the picture, there are 6 rectangles, right? But there's pairs of them, right? Because it's front and back, top and bottom, side and the other side. And they're the same, these opposite pairs are like the same size rectangles. So in our default formula that we need to write, we just start by writing 2 lots of L times W for like the first pair of rectangles, plus 2 lots of L times W, plus 2 lots of L times W, because we have 3 pairs of rectangles. And then you put your numbers in. Well, we have 2 lots of, if we do the forward rectangle, it's a 2 by 3. And then if we do the top and bottom rectangle, it's a 3 by 5. And then the other sides we're missing is the sideways rectangle, which is a 2 by 5. So if you put all that in the calculator or work it out in the brain, 2 times 2 is 4, 4 3s are 12. 2 3s is 6, 6 times 5 is 30, and 2 times 2 is 4. 4 times 5 is 20. So all that together gives us 62 centimeters squared. Centimeters squared because we're talking about area units. B is very much the same. So SA, surface area, equals. Start with default formula. So just, if you can imagine unfolding, like flattening that pyramid, what do you see? Well, on the base you have a square because it's a 2 by 2. So you have L squared. And then you have 4 identical triangles all around. And so the default formula for a triangle is base times height over 2. So you just put your numbers in. Side, the bottom of your square is 2. So 2 squared plus 4 lots of triangle. You're trying to find perpendicular height. Don't forget about that. So find a right angle, find the base, find the right perpendicular height, which is 2 by 3 divided by 2. So that's 4 plus 12, which gives us 16 meters squared because everything is in meters. So example 1's a pretty straightforward, simple question. You just literally add up the areas of every space you see. So you can't forget the like big page of the area formulas, that like those weird shapes, the kites and all that stuff, because you could get a weird shape as prism as well. Now the fun question is example 2, where it brings back memories of well, it's a nice word problem actually. It's just nice. I mean, we're lucky enough to give us a diagram. So example 2 says the rectangular piece of cardboard on the left has 4 squares cut out from the corners to make an open box whose dimensions are 30 by 20 by 15. Part A, what was the length and the width of the original piece of cardboard? So luckily for us, they've given us a diagram, so we just label the diagram given. So first they tell us that there are 4 squares, the corners, the dotted edges, so we can label the squares by indicating they have the same length with the dash. So all 4 corners have the same length, which we label with a dash, and they have the corner length of 15 centimeters. Or does it not tell us? No, actually, no, it doesn't tell us, but it's okay. But we know it's 15 because if the base... So the base of the rectangular prism is 30. So the horizontal distance across that base distance is also going to be 30. So that's 30 centimeters from here, this edge to that edge. We know that the width of the rectangle is, width of the rectangle base is 20. So we know this distance is 20. And we know that the height of the rectangular prism is 15. So that tells us the square edges are also 15 by 15 because that's the height of the rectangular prism. So that's why we know that these square edges are 15 centimeters by 15 centimeters. Because if you unwrap the box, it would be the height of the rectangular prism. So to answer part A, what was the length and width of the cardboard? Well, original length, it's the total length spanning to the whole edge. So that red edge there. So it's 15 plus 30 plus 30. 15 plus 30 plus 15, sorry. 15 plus 15, 30. 30 plus 30 is 60 centimeters. And original width is 15 and 20 and 15, which is 50 centimeters. Now the new, well, it's not really new, it's assumed like from year 8, we supposedly remember how to work out percentages. What percentage of the original piece of cardboard is wasted in making the box? So we first have to work out, well, what's the total area of the original piece of cardboard? Then we have to work out the area wasted, which are the corner squares, and then we can work out the percentage. So area of original is a rectangle, so it's length by width. The original rectangle is 60 by 50 because we worked that out in part A. You had to add on the 15 centimeters corners. That's 3,000 centimeters squared. If we work out the area of the wasted part, that's 4 lots of squares, so 4 lots of L squared. So that's 4 lots of 15 squared because all the squares are 15 by 15. Calculator says 900 centimeters squared. Now, this is the part where you have totally no memory of how to work out percentages, but that's okay. So, throw back to year 8 percentages. If you want to work out percentage wasted, you have to divide the area wasted by the area of the original, and because it's percentage, you multiply by 100%. So putting our numbers in, it's 900 divided by 3,000 times 100%. In a calculator, you don't type in the percentage signs, you just work out what 900 divided by 3,000 is, which is 1/3. Wait, no, that's not right. Well, just use a calculator. In the end, you get 30%. So, therefore, percentage wasted, or percentage of cardboard wasted is 30%. And we're done. And to-do list is on the bottom. Make sure you draw diagrams and sentence conclusions. And have fun.